first question on statistics. Does somebody want to read it, and then we can go through the answers? Does that work?
Why does the p-value tell you nothing about the alternative hypothesis?
All right, and let's go around. Do you want to answer?
I said it's because it's a value calculated based on the null, not the alternative.
Exactly, yeah. The definition of the p-value has nothing to do with the alternate hypothesis. It's just the probability of your data under the null. Exactly. All right, Caroline, next question.
Should I read?
Yeah, you get to read it.
When is it not necessarily a bad idea to use a significant threshold of 0.05?
No, Kim gets to answer. That's how we're going to round.
Oh. I wasn't too sure about that one. But that's like, I know that's if you don't mind taking that like 1 out of 20 chance that you might be wrong.
Mm-hmm. Exactly. And it's not just wrong once, it's wrong on every test that you do.
Yeah.
So if you do like 100 tests, you know you're going to be wrong 5 times, right? So maybe then you don't actually want to use a 5% significance threshold. Yeah, so the answer to this one is if you're only doing like 1 or maybe 2 tests, even if you do 2 tests, you should probably actually change your significant threshold as well, so that a statistician reading your papers will be like, oh wow, this person knows what they're doing. But in general, if you're only doing 1 test, yeah, 0.05 is fine. But once you start doing more than that, you start introducing possibilities of false discoveries. All right, Laura, next question.
If you do 100 independent tests where the truth is I can't read this question. If you do 100 independent tests where the truth is everything is null and you use a threshold of 0.05, what is your expected FDR and FWR?
Okay, so false discovery rate. So how do you calculate the false discovery rate?
So it's false positives over the number of positives.
Okay.
So I just thought it'd be 100% because if everything is null, then all of your positives are false positives. So every discovery is a false discovery.
Exactly. Yeah, your false discovery rate is 100% because you expect to have 5 false discoveries, and all 5 of those are going to be false discoveries. So, all right. Oh, and then family-wise error rate.
That I got 1 minus 0.95 to the 100.
Exactly. Whatever that equals that's going to be really close to 1. You have almost 100% chance of having a false discovery, or your family-wise error rate is going to be really high. So, all right, Rose.
100 undergraduates do psychology studies as part of their degrees. In each of their studies, they do 1 test, and they each use a significance threshold of 0.05. 9 of the students submit their results showing a significant result. How many of those 9 significant results do you expect to be true positives? How many false positives?
All right, Caroline.
So you expect 5 to be false positives,
Mm-hmm.
so 4 would be true positives.
Exactly.
Then that's it.
Say again?
Was that all?
I think that was it in that question.
The false discovery rate then be like 5 nines then?
The false discovery rate would be 5 9. Yes, yeah, 5 9 would be the false discovery rate, which is like a really high false discovery rate. And so the different fields of science have different amounts of problems when it comes to false discoveries. And psychology is one of the worst. Like a lot of times they'll do these studies and they'll get significant results and they won't replicate. And a lot of times that's not even just due to like statistical problems like this, but it's simply due to like population structure that they have or bias in sampling. So yeah, and so the fact that you see something significant once, it's kind of like, that's great. And then you ask for money to do it again. And that's basically how science works, is you see something, you think it looks significant, and then you ask money to do it again, which is what the next question is about. So, Kim, do you want to read the next question?
I actually don't really understand where we got
Okay.
5 and 4 for this.
So if you do 100 tests,
Right.
assuming they're all null, you expect 5 of them to be false positives,
Right.
right? And so the difference between what you expect to be false positives and the number of positives you got is probably how many true positives there are.
Sorry, can you repeat?
So you do 100 tests. Let's assume all of them are null.
Yes.
You expect 5 of them to be false positives,
Yes.
right? But now you do it and you don't get 5 false positives, or you don't get 5, you don't actually know what's a false positive and what's a true positive, right?
Right.
All you know is when you do 100 tests, if you're controlling at 0.05, you expect 5 false positives.
Yeah.
But you observe 9 positives,
Right.
right? So how many of those 9 positives do you expect to be true
Oh,
and
okay,
expect?
Sure.
Okay,
Okay, that makes sense.
yeah. All right, so Kim, you want to read the next question?
You asked the psychology students in the above question who had significant results to repeat their studies without using any of the same study subjects. How many of the 9 subjects above do you expect to replicate their significant results? How many will not replicate their results?
So, yeah, I didn't get to this one, but you wouldn't expect the 5 false to replicate their results, because 5% of 9 is not a very big number. Right, so like, it seems like the number of false positives expected for 9 tests is less than 1.
Exactly. And you expect that 4 of those 9 are actually true positives. So you expect 4 of them to replicate. And then those 5 that were false positives, yeah, if you do 5 times 0.05, you get like 0.25, right? So we're actually only expecting a quarter of one of the tests to replicate, if that makes sense. And this isn't completely accurate in that even if you do have a true effect, like something that was a true positive might still not replicate because you might not like sample enough individuals in your study to have power to make it replicate. So there's a whole bunch of other issues in here that I didn't go into, but kind of to like a ballpark approximation, you guys have got the idea. And so whenever you see all these studies online and they're like, we found that coffee does magic, you can be like, all right, how many studies are there that found that coffee did this? Like, is this just one study? And what significance? Because maybe that study used a 0.05 significance threshold, right? But how many other types of magic did they mix coffee with? Like maybe one study did coffee versus how long you live. Maybe one did coffee versus BMI. One did coffee versus grade attainment. One did coffee versus favorite color. Like, there could have been thousands of tests all using like a 0.05 threshold, but the only one that gets picked up in the news is the one that beat the 0.05 threshold. So the fact that you don't know how many other coffee studies were tested, like, that's why you have to be really skeptical when they're like, study found this, is because they're not reporting all those other tests that were done where they didn't get a significant result. And that's why basically they have all these studies that like, this cures everything. And then you never hear about it again because they try to replicate it and they're like, no, it doesn't. That's basically the story of pop science, also in case you were wondering. All right, next question.
When must you sample to determine an empirical null distribution?
Yeah, when must you sample? In other words, when can you not assume a distribution?
There's gonna be like other things affecting it.
Let's go for an example here. I want to know the distribution of shoe size. Can I assume a uniform distribution? No. Could I assume maybe a normal distribution? Most people are like, I don't know, 7s or 8s. A few people smaller, a few people, right? So I don't actually have to go and sample a bunch of shoe sizes, right? So that's when I can just assume a distribution. So when can I not assume a distribution? I'll give you an example and then you can give me an example back. What's the distribution of the types of shirts people are wearing at UCLA today? Long sleeve, short sleeve, polo, t-shirt, tank top. I have no idea. So I can't assume uniform, can't conserve normal. Basically, my only way to figure out what that distribution is to go and like stand out like in the court of sciences and like count everybody. So that's a distribution where I can't assume something because anything I would assume probably doesn't match reality close enough to be able to just ignore the fact that it's not perfect.
But then in that case, it would be due to the other factors that there are, right? Like it could be sunny outside or what's in style and like the age group and everything.
Exactly, and so that's why I'm saying like today I have no idea. Like tomorrow it might be different. And so that's the thing, like I can't assume anything today, I literally have to go out and measure it.
So you can only assume it when there aren't that many factors, like shoe size is just something you're born with and it's normal.
Yeah, shoe size will be affected by like diet and like physical activity and stuff like that. But in general, people kind of, we all kind of have the same average. And like if we, in our minds, we can imagine that the shoe size follows a normal distribution. And what we could do is we could actually do a little sampling. We could go sample 100 people and ask, of those 100, do you actually follow the normal distribution, right? And it would confirm our results and be like, yeah, yes, it does, perfect. And then we're done. Whereas if we're like, hey, let's go like, what are people wearing today? We could assume a distribution, like a uniform distribution, and go out and be like, oh, our distribution's all wrong. Like this doesn't follow normal, doesn't follow uniform, doesn't follow any of the other ones. And then we're just like, well, we can't assume anything. And then we have to go on and sample many, many, many people. So it's essentially just when you can't figure out when to assume. So why don't you come up with one? What's the distribution that you would have to go sample?
Another example?
Yeah, give me an example.
Maybe what kind of music people listen to in the headphones?
Yeah, exactly. Like we have no idea offhand what people are listening to. So we would actually have to go out and ask people and see what they're saying and build up a distribution. Yep. Yeah, so essentially whenever you're pretty sure that reality follows one of these known distributions, you can assume it. But if you're like, probably doesn't, then you have to use an empirical distribution. All right, is that last question or one more?
We just did both of those.
Yeah.
Okay, cool.